Welcome to the ultimate zero-to-hero guide on vector databases, where we'll dive deep into the technology powering modern AI. Databases have evolved over 60 years. We went from relational for structured data and exact matches to unstructured for text and media. Today, vector databases are born for AI, focusing on semantic meaning and similarity search. Traditional databases see data like a computer, focusing on exact matches. Vector databases bridge this semantic gap by understanding data like a human, recognizing meaning and context, even when keywords are missing. Relational databases are like spreadsheets, fast for exact matches but poor at abstract similarity. Vector databases are like a multiverse, storing embeddings, mathematical interpretations that understand concepts like electric cars without explicit tagging. A vector embedding is a long array of numbers representing learned features. By converting data into these numerical vectors, computers can accurately calculate similarity based on features like elevation, urban elements, or warm colors. Visualizing vector space, similar items are clustered close together on a semantic grid. For example, two different sunset pictures are neighbors because they share the feature of warm colors. Embeddings are created using powerful AI systems called embedding models. Models like Clip for images, BERT or GLOVE for text, and Wave2Vec for audio all extract abstract features and convert them into numerical representations. A major use case is retrieval-augmented generation, or RAG. This technique gives, quote, long-term memory to large language models by fetching real-time data from vector stores, fixing knowledge gaps, and preventing inaccurate responses. Phase 1 is ingestion, starting with raw data like PDFs or web pages. The crucial step is text extraction and cleaning. Only high-quality, noise-free content should be embedded, preventing, quote, garbage in, garbage out. Because you can't embed an entire document at once, a critical step is chunking. Small chunks are great for precise similarity search, while larger chunks provide better context for the LLM. Common chunking strategies include recursive chunking, which splits by paragraph, and semantic chunking, which uses AI to cut when the meaning shifts. It is also important to use overlap strategy to preserve context at chunk boundaries. Once data is in vector form, we measure similarity using metrics like Euclidean distance, the straight line distance. Cosine similarity measures the angle between vectors and is most common for AI, as it focuses on direction, not magnitude. A key difference is seen in recommendation systems. If user A watched 100 sci-fi movies and user B watched 5, Euclidean distance says they are different. Cosine similarity correctly says they are identical in preference because their vector angle is the same. The core challenge of scale is the curse of dimensionality. Comparing a search query to millions of high-dimensional vectors is computationally expensive. The solution is approximate nearest neighbor, or ANN, indexing. The hierarchical navigable small world, or HNSW index, is a top-performing graph index. It creates multi-layered structures, using top layers for fast jumping and bottom layers for fine-tuned search, scaling logarithmically. The inverted file index, or IVF, partitions the vector space into clusters using centroids. It's more memory efficient than HNSW, restricting searches to nearest clusters, although it can be slightly less accurate. To handle massive data, we use sharding. This, quote, divide and conquer approach splits the data across multiple servers, or shards, allowing the database to search billions of vectors simultaneously in milliseconds. Replication ensures high availability. Vector databases create redundant replicas, or workers, to increase throughput and handle requests in parallel. If a primary machine fails, a replica instantly takes over, ensuring the application remains available. A vector database is a full database management system, supporting CRUD operations for dynamic data. It offers language bindings for Python, the primary language for AI, as well as JavaScript and Java for enterprise applications. The first use case is recommendation systems. Traditional systems require manual tags, but vector databases automatically analyze user profiles and subtle similarities. This results in better suggestions on platforms like Netflix and Spotify. The second use case is media understanding and visual search. AI extracts features from pixels to find images based on content, not file names. This has applications in medical imaging, surveillance, and real-time traffic analysis. The third use case is anomaly detection, which is the opposite of similarity search. By identifying vectors far from the normal cluster, vector databases can spot fraud, like sudden, unusual spending patterns. There are two main types of vector implementations: native vector databases, built purely for vector workloads, and vector-enabled databases, which add vector support to an existing database management system. A major challenge is semantic drift. Language and trends evolve, meaning a word's context can change over time. Models must be regularly fine-tuned or retrained to keep up with this evolving semantic meaning. Computational costs are a significant factor. Running embedding models requires high-performance GPUs, placing massive pressure on hardware. Cost optimization and cloud scaling are essential parts of the vector database engineering lifecycle. To summarize, vectors understand meaning, not just keywords. RAG pipelines build smarter AI with real-time memory. HNSW and IVF indexing allow searching millions of vectors quickly, making vector databases 100 times faster for AI tasks. If you're ready to build, consider subscribing to Dev Basics with AI and check the description for links to the tools mentioned in this video.